Howdy, folks. And it is time for us to learn some more chemistry. I really wish you were here in person. It's going to be a quiet couple weeks, I'm afraid, but we will manage, won't we? We will carry on. We will just keep pedaling, as we like to say in AP chemistry. So, I hope you've watched the video on galvanic cells, and if you had, then you would say, okay, we have a couple of half cells, right? And you have some electrodes in those half cells, and you got usually some solution, and those half cells are connected by a wire, and you have an anode, or you have an anode which sits in your oxidation half cell, and you have a cathode that sits in your reduction half cell, and you have the electrons flowing from the anode to the cathode, right? Electrons are going in here. Over here, I have something that is giving up electrons and is oxidizing, right? And those electrons travel up through the wire and they come down here. And then I have something over here which is picking up those electrons and maybe plating onto my cathode. And the question might be, why? Why are electrons floating or flowing through the wire from the anode to the cathode, right? And so that's what we want to talk about right now. And that would be called our electromotive force. So let's get into some notes. We want to eventually, big three is going to be E cell not, which we would call the standard cell potential, standard cell potential. Okay, and where we want to start here is with our idea of electromotive force, right? Electromotive force, EMF. I always thought if I had a rock band, I'd name it that, electromotive force, and I'd be the lead singer, Max Power, right? And what do I mean by what is electromotive force? Well, the electromotive force is the reason why, uh, this is the reason why electrons flow in our cells, in our galvanic cells. By the way, it also is the reason why electrons flow from one thing to another in all redox reactions. Remember, galvanic cells are just redox reactions. So when we're talking about galvanic cells, much of what we're talking about also applies straight to redox. The thing about it is, in our cells, there is a difference in potential energy between my anode and my cathode, really, between my oxidation half cell and reduction half cell. And like there's a difference of potential energy between the top of a mountain and the bottom of in a valley, and as a result, water flows from the top of the valley from the top of the mountain to the valley. That's also true about my potential difference in my galvanic cell. The reason that electrons flow from my oxidation half cell to my reduction half cell is because of the difference in potential energy. My oxidation half cell is at a higher potential energy. And so that is really my driving force. And so what is my EMF? My EMF is the difference in potential energy per unit charge between two bodies. All right, so that is my EMF, and this EMF, the EMF drives the electrons through the circuit in a galvanic cell. All right, cool. Now, we might want to talk a little bit about what is the, oh my gosh. All right, we'll just keep flowing, right? I've already messed up my outline, but you guys will kill me if I go back. So let's talk about the unit. What are the units for my EMF? Well, they are the volt. Volt is my standard unit for electromotive force. And just to clarify that 1 volt is equal to 1 joule per coulomb, right? A joule is what? Energy per coulomb is charge. Great, wonderful. Good, moving on. So now let's talk about our next thing here. And I'm going to need more space, aren't I? Give me some more space. Why do you not work for me? There we go. There we go. Good. I have no idea. I better look up and see what's my outline. I'm on A. What's B? Cool. So let's talk about my cell potential. E cell. All right. So this would be my electromotive force for my galvanic cell. It's also called cell potential. And it's really pretty easy stuff. Depends on, it's a function of 3 things, right? It's a function of my specific reaction, my concentration of reactants, the concentration of my products. Oh, what happened? Concentration of my products. And finally, my temp. These things all have a function, all have an effect on my E cell. One other thing that we might want to throw in here is that for my cell to actually function, for redox to occur, my E cell has to be greater than 0, right? Cool. Now, what about, I don't like this so much. I have to keep going back up. I can't see B. Oh, there we go. B is E cell, so C would be E cell prime. And that would mean what? This is my E cell at standard conditions. And we might want to know what standard conditions are. And that would be 25C, 1 atmosphere, and my concentrations of my reactants equal the concentration of my products, which are equal to 1 molar. All right, so I have my E standard, and now once I have my standard cell potentials, I'm going places, right? I think I'm going places. By the way, why are we doing all this? Anybody recall? Well, we want to figure out what is the standard cell potential for a galvanic cell made up of iron 2 and nickel 2, right? So that's why we're going through all these notes so we can answer those questions. There we go. Man, I have to expand the page again. Yikes! Good. So then, let's talk about half cell potentials. Half cell potentials. We love half cell potentials, and the reason for that is half cell potentials. We have tables for them, but what's a half cell? Well, that is the electromotive force, the EMF for uh, oh, sorry, let me back up. The EMF for a cell is really a function of, depends on the half cell potentials. The potential of each half cell. All right, cool. And so then we could figure out the cell potential by looking at each half cell. And the beauty is there are tables for standard reduction potentials for half cells. Now notice that these are standard reduction potentials. We know that in a galvanic cell that one half is oxidizing and another half is reducing. But however, for these tables, they are writing everything as if everything is reducing. As a result of that, we kind of play a little trick here in our calculation. So if we want to know the standard cell potential, we are going to take the half cell potential, the standard reduction potential at the cathode, at the reaction happening at the cathode. And what reaction is that? That's the reduction half cell, right? That's the reduction that is occurring, minus, instead of adding, because these are both written as reductions, we're going to subtract the standard reduction potential at the anode, i.e., what is happening in the oxidation half cell, right? The oxidation half reaction. So based on that, then we can calculate a cell potential. The standard half cell reduction potential, the standard reduction potential is based on hydrogen. And so the hydrogen would be what? 2H plus aqueous, 1 molar, right? Is going to react with 2 electrons to produce H2 gas, and that's got to be 1 atmosphere. And of course, it needs to be at 25C. And when we do that, based on this, my standard reduction potential is equal to 0 volts. All right, so that is our standard. One other thing we might want to know is the greater this difference, ay caramba, the greater the standard cell potential. So the greater the standard cell potential, the greater the driving force. Force for the reaction. All right, sound cool? One other thing about standard reduction potentials is that my standard reduction potentials are what? An intensive property. What does that mean? They're independent of amount. So if you double the coefficients in your half reaction, nothing happens to the standard reduction potential. Watch that. That will be a trick on the AP exam. All right? Cool. I guess I should add one other thing here, right? As my E cell goes to 0, the reaction stops. All right, because I no longer have a driving force. Cool. Let's see one other thing, and then maybe we will answer some questions. Uh, in in a galvanic cell, I can always figure out which thing is my reduction half cell, because in my galvanic cell, the um, cathode is always in the cell with the higher standard reduction potential. All right? So for instance, if I have a cell and I don't know which one's the cathode or the anode, I simply look at the standard reduction potentials. The one that has the higher standard reduction potential, that's the one that's going to be my reduction half reaction, and so that will be where I can find my cathode. All right? Good. Now what am I talking about in terms of standard reduction potentials? Well, right here are a bunch of standard reduction potentials. Oh my gosh, my eyes hurt just looking at this. But, you can look around and we can see, remember I said there are certain things that tend to be oxidation agents. You take a look at something like my dichromate. There should be a 2 there, by the way. My dichromate has a standard reduction potential of 1.33. That's a very high standard reduction potential, meaning it is going to almost always do what? Reduce, meaning it's going to make something else, such as copper here, which has a very positive standard reduction potential, but not very positive, but not as big as my 133. So it will cause my copper to not reduce, but to flip around, and my copper will oxidize. All right? Cool. I think we can answer a question. Let's go try to do it. Oh, here we go. It would be so much more fun if you guys were actually here. All right, so I have this galvanic cell, and it's composed of iron and nickel. And what is the cell potential? So I have what? I have iron solid, right? And iron solid is going to go to my iron 2 plus 2 electrons. And we said my nickel 2 was going to gain 2 electrons and go to nickel. And so now we need to find their standard reductions, right? Now remember, although this is written as an oxidation, I'm still going to look up its reduction potential. So let's find iron 2 going to iron and nickel 2 going to nickel. Well, actually it's the opposite way. Here's iron 2 going to iron. That is 0.44, negative 0.440 volts, right? And then where's my nickel? Let's find nickel. So here's my nickel reducing, and it's a negative 0.28, negative 0.28. Is that a 280 volts? No, just 28 volts. Cool. So now I can go back here and I can answer my question. My 2 are what? A negative 0.440 volts. This is a negative 0.28 volts. How do I get my E cell? My E cell is going to be my standard reduction potential at the cathode minus the standard reduction potential at the anode, right? AKA at the cathode, what's happening? This is for my reducing species, and here is my oxidizing species. Good, so which is which? Since this is a galvanic cell, it's pretty easy. The one with the higher standard reduction potential is going to happen at the cathode. So I have a negative 0.28 volts minus my negative 0.440 volts, and that is what? A positive 0.16 volts. I hope so, man. I'm flying without a calculator here. What if I can't add right? And you guys know that that happens on occasion. So I'm going to take a negative 0.28 minus a 0.44, and I get a, what in the heck is that? Wow. It looks like a mess. Negative 0.28 minus a negative 0.44, and they get a positive 0.16. Cool. All right. I'm going to put you guys on pause and let you do the next one. This one right there. Go to it. All right. Put me on pause. Bring me back when you're ready. All right. I'm ready. So what do I have here? I have zinc, right, which is going to lose 2 electrons, and that is happening at my anode because this is oxidation, and yeah, you guys have already done this in the other previously, right? I'm assuming you know that this is the case. And then what's happening? My copper 2 plus aqueous is gaining 2 electrons and is going to copper solid, and this is happening at the cathode, right? Cool. So we need to look at my standard reduction potentials. So let's look at my standard reduction potentials. Go back to my chart. I need zinc and copper 2. And so what's my standard reduction potential for zinc? Ooh, mama. It is what? 0.763, a negative 0.763 volts for my zinc. And what about for my copper 2? My copper 2 is a positive 337, positive 0.337 volts. So here we go. Let's back this up. Yoink, yoink. Oops, got a forward. Here we go. My standard reduction potential is a negative 0.763 volts, and my copper is a 0.337 volts. So what am I going to do? My standard cell potential is equal to my standard reduction potential at the cathode, meaning my reducing species minus the standard reduction potential at the anode. That would be my oxidizing species. So that means I'm going to take a 0.337 volts minus a negative 0.763 volts. Okay, 0.763 plus a 0.337. Yoink. 0 carry the 1, 0 carry the 1. Holy moly, is that correct? 1.100, 1.100 volts would be my answer, right? 7 and 3 is 10, carry the 1. 6 and 9, 10, carry the 1. That would be a 0. No, that would be a 1. Yeah, that's right. Cool. I think that's right. I'll tell you what, we've been going for 23 minutes. Why don't we stop here? Bring me back for the next lesson. All right? See ya.